In this video I'm going to go over something known as isomerism or isomers, and I did mention this in an earlier video as one of the definitions you should be aware of. So just to remind you of what an isomer looks like, or an isomer is by definition, an isomer then is a group of molecules or molecular compounds with the same chemical formula but different chemical structure. And we're going to look at two types of isomers. One type are known as constitutional isomers or structural isomers. So this is just where there's, say, a methyl branch in a different spot or something like that. And then we're going to look at one specific type of spatial isomer, and it's known as a stereoisomer. And so you'll see what stereoisomers look like in a bit. Just to draw your attention to this Chem Guide website again, they go through this reasonably well as well if you'd like to look at it in a slightly more static way. So let's get stuck into this. So constitutional isomers or structural isomers, basically the isomer differs in the position of branches is one way to look at it. So you can have branch at a different spot. The position of a double or triple bond, so this occurs with alkenes and alkynes, so just moving along the chain. And the position of a functional group, and we haven't talked about functional groups yet, but the functional group can just move down the chain as well. And finally, look at isomers caused by the functional group splitting or changing, and we're not really going to get into that too much, but that is a possibility. So here's one example. So chain isomerism, where you have a butane. So there's my butane, 1, 2, 3, 4 carbons, straight chain butane. Well, if I was to make that a 3-carbon chain, so now it's a propane and added a methyl branch, that is an isomer. And I can very easily tell why that is an isomer because, I mean, it doesn't look necessarily much the same, which is a feature of isomers, but I want to check that the chemical formula is the same, because if it has the same chemical formula and the structure is different, that's an isomer. So let's just quickly do the math here. So how many carbons do we have? 1, 2, 3, 4. So that's C4, H3, 7, or 5, 7, 10. So C4H10, alkane. And how about this one? 1, 2, 3, 4 carbons. So that's also C4, H3, 4, 7, 10, H10. So those are isomers. So butane and 2-methylpropane are isomers. And that is because of the different chain length, but the feature or fact that you have branches. Positional isomerism then takes branches and places them in different spots. So again, let's look at this one. So 2,3-dimethylbutane. So if we counted the carbons, let's call this carbon 1. There's carbon 1 to carbon 2, so there's a branch on carbon 2. Carbon 3, there's a branch on carbon 3, and there's carbon 4. So 2,3-dimethylbutane. Well, 2,2-dimethylbutane is going to be an isomer. So I'm going to draw this a little differently. The easy way to draw butane, straight chain butane, 2,2-dimethyl. There's carbon 2, and I'm going to add a methyl group. And there's carbon 2. I'm going to add a methyl group. And I'm going to add hydrogens the rest of the way. And there we go. So that's a pretty straightforward isomer. It shouldn't be hard to see that. Position of branches. Okay, position of multiple bonds. So this is positional isomerism. So these two examples show a differing position of a bond leading to isomerism. So but-1-ene is shown there. So there's carbon 1 to carbon 2. So that's what the 1-ene means because it's a double bond. 3, 4. So it's a 4-carbon molecule, but. So but-1-ene. So but-2-ene, how would I draw that? Well, again, to do it simply, there's my 4-carbon but. 2-ene. So carbon 2 now has the double bond to carbon 3, and I would add hydrogens to saturate that. And again, I can do a quick check to see if they're still balanced or still have the same chemical formula. 1, 2, 3, 4. So C4, H2, 3, 4, 5, 8. And C1, 2, 3, 4, H3, 4, 5, 8. So they are isomers because the chemical formula is the same. So positional isomerism based on movement of a double or triple bond is quite common. This is another example of a positional isomer with the functional group being positioned differently. And so if we look at this particular, you haven't come across the alcohols yet, but we will shortly. Propane 1-ol, carbon 1, 2, 3. So the 1-ol telling me my OH group, my hydroxyl group, is off carbon 1. And so a simple isomer is that, just move that OH group to carbon 2. So here we are here, 1, 2, 3. So propane 2-ol. So the functional group is just on a different carbon. And obviously there wouldn't be a propane 3-ol because we would just start counting from the carbon 1 where the functional group is not the third carbon. So positional isomerism can also include movement of functional groups. Functional group isomerism, so again, this is where you actually have different functional groups or different types of structures, but because of the arrangement of the bonding, you end up with isomerism. So these two particular isomers, it's not easy to tell unless you start counting things. So cyclohexane, cyclic hydrocarbon, let's get the chemical form. So it's a hexane, so it must be C6, H, 2, 4, 6, 8, 10, 12. C6H12. So cyclohexane formula C6H12. Well, how about pent-2-ene? 1, 2, 3, 4, 5. Wrong molecule. Should be hex-2-ene. And I'm going to add that third or sixth carbon. So hex-2-ene. 1, 2, 3, 4, 5, 6. So 6 carbons. H, 3, 4, 5, 6, 7, 8, 9, 12. C6H12. So cyclohexane and hex-2-ene are isomers because they have the same chemical formula and they are clearly structurally quite different. So that's a good one to remember. Cyclic alkanes and same chain length alkenes will be isomers. That's one people often overlook when looking for isomers. Okay. Cis-trans. So cis-trans isomerism is this type of stereoisomerism, or basically an arrangement around bonds that leads to structural difference. And a component of this is the fact that you have a double bond. So C double bond C, as we've ascertained, there's no rotation about that bond, so it's kind of fixed, and that means anything off the carbons in terms of orientation will be fixed. One thing to talk about first is what are known as ligands. And so here's our carbon-carbon double bond. And so we talk about ligands off the carbons of the bond. And so ligand is just a carbon-containing group, like a CH3. So this would be known as a ligand. And so for this molecule, which is propene, propene only has a single ligand off the carbon-carbon double bond. There is no ligand off here. H2 is not a ligand. Okay, so propene only has one ligand, whereas we look at this one, this is pent-2-ene. So pent-2-ene, if you look at the ligands or look at the carbon-carbon double bond, does it have ligands off both carbons? Yes, it does. So there's a ligand and there's a ligand. Okay, so pent-2-ene does have ligands off both carbons of the double bond, and that sets up the fact that pent-2-ene can exhibit cis-trans isomerism, whereas propene does not. And so here's why. Alkenes must have carbon-containing ligands bonded to each carbon of the carbon-carbon double bond to be a stereoisomer. So again, if we quickly go look at the ligands, here's a double bond on carbon 2 to carbon 3. There's a ligand and there's a ligand. So this will exhibit cis-trans isomerism. This is in fact trans. And so it's called trans but-2-ene. So trans is basically, I think, comes from the term transverse, which these are on opposite sides of the organized oppositely on opposite sides of the carbon-carbon double bond. Because there is no free rotation around this double bond, it cannot rotate. They're fixed like that. So the ligands will always be in that position for trans but-2-ene. And so if you look at the other side of things, again, no free rotation around this carbon-carbon double bond. And so these ligands are orientated in a different position, and so this is known as cis, and so this is cis butene, and it is clearly structurally different. So that is cis trans isomerism, due because there is no free rotation around a double bond. That's why cis trans isomerase gets set up. But again, you must have a ligand off each of the carbons of the double bond before you can get cis trans. So here, again, just to look at it from a structural formula point of view, here's a few structural formulas. If you have a C6 or C4H8 molecule, it can look like this from a structural formula point of view, and that's this one first. And there's only one option for that if you start drawing it. So we have two hydrogens bonded to carbon 1, carbon 2 with a single hydrogen. Well, that must be a double bond. CH2, CH3. That's the only possibility, and so that is not cis trans isomerism. So that is just known as but1ene. However, if we go to the second one, so this one has CH3, CH, CH, CH3. And so if you start drawing that, CH3, carbon 1, carbon 2, C with a single H, carbon 3 with a single H, carbon 4, CH3, well, the bonding is not satisfied in carbon 2. And so there's the double bond. And if you look at this, this does not show cis trans isomerism. So as I say down here in red, you have to show the three-dimensional bonding, or try to show the three-dimensional orientation off the double bonds to show cis trans. But it's really quite straightforward, so I'm just going to get rid of this one and we'll start again. And here's how I do it. So we know it's going to be on carbon 2. So draw carbon 2 with the double bond first, and I have a single carbon off each one. So here's how you can show three-dimensionality. Boom. Three-dimensionality, H3. If you want to draw cis, same side, and there it is, and then add the hydrogens. So this is, again, cis butene versus double bond in the middle, trans. So there's trans, I'm going to do the opposite. That is showing three-dimensionality around the carbons of the double bond, and it is required if you're going to show cis trans isomerism. Two more examples to finish off. Cis oct 4ene. So cis tells us the orientation around the double bond, and the 4 tells us the double bond starts on carbon 4 of an 8 carbon chain. So let's start with carbon 4. There's carbon 4. So this is carbon 4 and carbon 5. Just to give you the idea, and it's cis. So carbon 3, if I do it like that, goes down. So that means carbon 6 will also go in. So there's my cis orientation. And then after that, you can really do whatever you want. So that's 4, 3, 2, 1, 6, 7, 8. And then add hydrogens. But again, that has shown the three-dimensionality that is required to indicate a cis geometry. So cis oct 4ene, trans hept 3ene. Well, it's trans and it's hept. So carbon 1, carbon 2, carbon 3 down. So this is the other way you can show it. And then across. So 3 to 4, 5, 6, 1 to 7. Okay, so that also shows the three-dimensionality. And there's my trans component. So a couple ways you can show three-dimensionality, but as I said, you must show the three-dimensionality when drawing cis or trans. A straight chain, cis or trans, doesn't work. You cannot tell the geometry around the double bond, which is what you're trying to get across. Yep, that's right, that's 7. Okay, I was just checking. Okay, so that's a quick little intro into isomerism. So that concludes this video.